तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we saw how the Fourier transform method can be employed to evaluate the transients in a network. A few comments about this method. Essentially, when we wish to find out the transient behavior of a network, it is generally after a switching operation. Let us assume that some excitation function is introduced into the circuit at t equals 0. And we wish to find out the response of the network following the switching operation. We shall make two assumptions. First of all, let us assume that the network is initially relaxed. That means it has no initial energy stored in the network, which in other words means the capacitors are initially uncharged and the inductors carry no current. This assumption of the network being initially relaxed does not entail any loss of generality, because if indeed there are initial charges on the capacitor and initial currents in the inductors, they can be replaced by equivalent sources, and these equivalent sources can be considered to be additional excitations, and the principle of superposition brought into play to evaluate the responses to the various excitations and adding them up to find the total solution. Therefore, we shall assume that the network is initially relaxed, and we are interested in finding out the response of the network following the switching in of an excitation at t equals 0. A second assumption we will make is that the natural response of the network is one such that it dies down to negligible proportions in course of time, and this is common to most networks that we deal with, particularly dissipative networks, and therefore this once again does not seriously disturb the generality of the situation. However, the Fourier methods can also be applied where the natural frequencies of the network have zero real part. In other words, there is sustained natural response, oscillations, sinusoidal oscillations, or a DC component, but the analysis becomes a little more complicated, but we will avoid situations of this type in this course. That means we will assume that the natural response decays with time. Under these assumptions, when we have a excitation switched in at t equals 0, we expect the response also to be 0 for t up to t equals 0, because the network is assumed to be causal, and therefore any excitation that is applied at t equals 0 cannot produce a response prior to that. So we expect the response to be 0 for up to t equals 0 and then become non-zero from t equals 0 onwards for positive t. Now the Fourier method tells us that any such excitation function can be split up as the sum of tiny sinusoids starting from t equals minus infinity onwards and going up to t equals infinity. Now each one of these sinusoids produces a response which can be evaluated using the steady state sinusoidal circuit theory methods, that is using these frequency response techniques, and then all these responses can be added up to find the total response. So the sum of the steady state responses is what we obtain through the Fourier integral approach, and it turns out that the sum of the various steady state responses for the types of networks that we have talked about is also will become 0 up to t equals 0. So this is as it should be, because no response can occur before the application of the excitation. And we further observe that if there are any natural responses terms produced at t equals minus infinity at the time where the excitation starts, all the sinusoids start from t equals minus infinity, all these natural responses will decay to negligible proportions by the time t equals 0 arrives, and this is the period in which we are interested in. We are interested in finding out the behavior of the network from t equals 0 onwards. That means the natural response terms which might have emanated at t equals minus infinity would have decayed to negligible proportions when we come to t equals 0 onwards. But the sum of the steady state responses that we obtain will include transient terms, natural responses starting from t equals 0. That is what we are really interested in. So the steady state responses will add up to 0 up to t equals 0, and from t equals 0 onwards the response that we get, the total response that we get, include not only the forced response but also the transient response or the natural response of the network starting from t equals 0. That is how it goes. Now let us take a second example to illustrate the application of the Fourier theory to a network or a system which is characterized by its frequency response. So let me take a filter network and see how the Fourier theory can be applied to this network. Let us consider an ideal low pass filter. And we apply a unit step function as its excitation, and we would like to find out what the response is. Now the ideal low pass filter has a frequency response function like this. So the frequency response function of the ideal low pass filter can be considered to be 1 for omega magnitude less than omega c and 0 for omega magnitude greater than omega c. That is, this is the kind of response function that we have. Now under these conditions, this is the system function of the low pass filter. Therefore yj omega, the Fourier transform of the output, is hj omega, the system response function, frequency response function, times the Fourier transform, this is hj omega, times the Fourier transform of u of t, which is the input function. Therefore this will be h of j omega times the Fourier transform of the step function is 1 over j omega pi delta omega. So this is y of j omega. If you find the inverse Fourier transform of this, you would naturally get the y of t. This is what we are interested in. So y of t is obtained as 1 over 2 pi from minus infinity to plus infinity of h of j omega times 1 over j omega plus pi delta omega d omega, sorry, e to the power of j omega t d omega. This is the inverse Fourier transform function. Now we are integrating with respect to omega, and we know that h of j omega vanishes when omega magnitude exceeds omega c. Therefore we need to carry out this integration from between the limits minus omega c to plus omega c, because outside the integral vanishes. Therefore this minus omega c to plus omega c, 1 over j omega plus pi delta omega e to the power of j omega t dt d omega. Now we observe, as far as the second term is concerned, pi delta omega multiplied by e to the power of j omega t d omega. Now the multiplying factor for delta omega, we can substitute omega equals 0 in that. Therefore this becomes 1, and we are integrating a delta omega over the range which covers omega equals 0. Therefore that results in pi. That means the result of this portion of the integration will result in pi, and therefore that pi multiplies by 1 over 2 pi will become half, plus you have minus omega c to plus omega c, e to the power of j omega t can be written as cos omega t plus j sin omega t divided by j omega d omega. Now, this portion cos omega t divided by j omega is an odd function of omega, and we are integrating between symmetrical limits from minus omega c to plus omega c. Consequently, this being an odd function and you are integrating between symmetrical limits minus omega c to omega c, the contribution of this portion becomes 0. Therefore, the contribution arises only from sin omega t by omega term, and sin omega t by omega t is an even function of omega. Therefore, I can write this as 2 times 0 to omega c sin omega t by omega d omega. That means this will become y of t becomes half plus 2 times, we must have also 1 over 2 pi from this, because 1 over 2 pi times this one we must have. So, 1 over 2 pi I must have. So, 2 times 2 pi 0 to omega c sin omega c t by omega sin omega t by omega t omega, or this is half of 1 over pi. This can be put as sine integral of omega c t. This can be put like this 1 over, because after all I can write this as this, I can introduce a t here and then d omega t here, and this can be thought of as sin theta by theta d theta, and once you have this taken as theta, the limit will become omega c t. So, this can be put in this form. Now, if you evaluate this, you have this is a constant dc term. As far as sine integral is concerned, you recall the sine integral will have a characteristic like this. It goes to pi upon 2 and minus pi upon 2. This is sine integral of theta, which we have thought of, we have discussed earlier. So, but this is multiplied by pi. That means this quantity will reach asymptotically minus half for negative values of time and plus half for positive values of time. So, if you add to that this half, eventually y of t will be like this. There will be some oscillations like this, and essentially eventually this reaches 1, and this is t, this is y of t. So, this will be the response of the ideal low pass filter for a unit step input. So, if you have a unit step input here 1, the output will be like this, and depending upon the cutoff frequency omega c for the low pass filter, if you make the omega c larger and larger, this will become more closer to the step function. That means the overshoots, the oscillations will reduce, and this portion of the curve will become steeper and steeper. So, the more the cutoff frequency of the low pass filter, that means the greater bandwidth for the low pass filter, it becomes closer and closer to this. But the interesting thing is, you are applying a sine wave like this. Actually, the excitation function is 0 up to this point, and you are applying, this is your u of t, but the response is non-zero for negative values of time. So, even before the excitation is applied, there is a response. So, this clearly shows that this is a non-causal system, and which means physically this is something which we cannot expect to achieve in the physically, and therefore, an ideal low pass filter that we are talking about here with this type of characteristic can only be approximated. It can never be realized in practice, because we believe that no physical system can give response even before the excitation is applied. So, this is a non-causal situation, and this is one way of showing that an ideal low pass filter of that particular characteristic is not achievable in practice. All one can do is modify these characteristics in such a way that this portion of the response is avoided. That means, all low pass filters that we can build in practice cannot give this type of response. It can only give a response. Suppose this is the input, it can only start giving response from this point onwards, maybe something like this, but this can be avoided. That means the ideal low pass filter characteristic cannot be obtained in practice. However, my point in showing this, giving this example is that Fourier transform methods can be applied to networks characterized in terms of frequency response as here, and is a very convenient tool in such situations. As an illustration of the application of the Fourier transform method, let us consider one application which is referred to as the sampling theorem. Okay, let us consider a function of time like this, which is band limited, in that the Fourier transform for that is confined to maybe like this. So, the Fourier transform is 0 for values of omega beyond omega h, or we can say that the highest frequency component that is present in f of t is omega h. No component of frequency beyond omega h on the positive side and minus omega h on the negative side exists in this particular f of t. Such functions are called band limited functions, band limited f of t. That means the frequency band of the components that exist in f of t are limited to this band, nothing beyond that. Suppose we do not consider this f of t for the entire time duration, but generate from f of t a sampled version of that. That means this is the f of t variation. You do not consider the entire variation, but take samples from that for tiny intervals like this. Tiny intervals like this. So, we consider f of t for small intervals of duration d and the period between two successive samples is t naught. This we may call the sampled version of f of t. We will call that f star t. This is a sampled version. So, notice f of t is a continuous function of time. We are considering a sampled version. We are taking samples each time for a duration d and taking the interval between successive samples is t naught. Now, it turns out that the Fourier spectrum of the sampled version will be something like this. If this is the original Fourier spectrum, the f star of t, the Fourier transform for that will be the same spectrum is repeated endlessly in both directions with a reduced scale factor. If this is omega h, this is minus omega h, and if the sampling period is t naught, and let omega naught be the corresponding angular frequency, then the next section is centered around omega naught, this is omega naught, and this is the other section is repeated at 2 omega naught, and so on. So, endlessly it goes in both directions. That means the sampled version incorporates in it the Fourier transform of the original signal to a reduced scale. Besides, it contains several other reproductions of the same original spectrum at a different scale. Now, imagine that the sampled version is put through a low pass filter, so that we select only this portion of the spectrum. that means we lift this spectrum out of this assembly of spectra, sections of spectra, and consider only this portion and avoid all the others by putting this sample version through a low pass filter. Then the spectrum of this, which is resulting the output of the low pass filter, is the same thing as this spectrum except for a scale factor. In other words, the low pass filter output would be a replica of f of t reduced by a certain scale factor. So it tells us that if we have a band limited function f of t, if you sample it in this manner, this sample, from this sample you can extract the original function f of t, even though you have missed out on the variation in the intervals in between. It does not really matter, as long as this is a band limited function. From the sampled version you can recover the original signal. And this is very important in communications, particularly because if you take these samples wide apart, then in the blank periods you can send other messages in the same communication channel. So a communication channel can be employed to send several messages in succession. So you sample one particular message and then send it at regular intervals, and in the blank periods you can send another message, a second message, a third message, and so on and so forth. This interleaving of these messages over the same communication channel is referred to as time division, time multiplexing, and this is a very common occurrence to effectively utilize a communication channel to send several messages which are inherently band limited in character. Now you can see, in order for us to be able to lift this section of the spectrum from and remove the others, you must have your low pass filter characteristic something like this. So if the cutoff of the low pass filter is omega c, then omega c must be larger than omega h, but at the same time you do not want to pick up any portion of this spectrum. So if this is omega naught, you have omega, this must be omega naught minus omega h. So you must be able to choose an omega c which lies in between omega h and omega naught minus omega h, which in other words means omega as the cutoff frequency must be less than omega naught minus omega h and must be greater than omega h. And this is possible only if omega naught is greater than 2 omega h. So only if omega naught is greater than 2 omega h, you will be able to pitch in on a suitable cutoff frequency for the low pass filter, because omega naught minus omega h must be larger than omega h. In other words, what it says is your sampling frequency omega naught must be more than twice the highest frequency component that is present in your original signal. Omega naught must be larger than omega h. If it is so, then you can choose a low pass filter and allow this sample version to go through it, and out comes a version, a continuous function of time, which is a faithful replica of your original f of t. I have not gone to the mathematics, I am just trying to explain how it works out. To complete the mathematics, let us see what it means is, to get this sampled version from f of t, all you have to do is multiply f of t by a pulse train. So if you have a pulse train of duration d, we will call this ps of t. Let us say, for the sake of generality, an amplitude a, duration d, and a period t naught. So if you have such a pulse train, you multiply the f of t by this pulse train, you get f star of t. So f star of t is ps of t, the pulse train, times f of t. Then we can find out the Fourier spectrum of f star of t. We will go to the mathematics now and show that this is indeed the type of spectrum that we get for f star of t. Let us see. Ps of t is a periodic pulse train, therefore it can be expanded by means of Fourier series, and we have done this type of expansion several times in the past. So let me straight away put down ad by t naught sine n omega naught d by 2 divided by n omega naught d by 2 is the Cn coefficient multiplied by e to the power of j n omega naught t, that is the time variation. N ranging from minus infinity to plus infinity is your Fourier series expansion for Ps of t, the periodic pulse train. Now, f star of t is Ps of t multiplied by f of t. So, which means that it can be written in this fashion as the sum of several terms sine n omega naught d by 2 by n omega naught d upon 2 e to the power of j n omega naught t times f of t. So, f star of t can be thought of as a infinite sum of several times, and this is the portion which depends on time. The rest of it is purely a coefficient. Now, to find out the Fourier transform of this, we can find out the Fourier transform of each individual term and add them up. And since this is a purely a constant as far as time is concerned, so we can write this as n from minus infinity to plus infinity of a d upon t sine n omega naught d upon 2 by n omega naught d upon 2. If the Fourier transform of f t is f of j omega, we have seen that the Fourier transform of f of t multiplied by e to the power of j n omega naught t is simply f of j omega minus n omega naught. That is, multiplication by an exponential in the time domain is equivalent to translation in the frequency domain. This is something which we have done. Now, let us see what we have got. F star of j omega, the Fourier spectrum of the sampled version, consists of several terms like this: f of j omega minus omega naught, f of, when n equals 0 it is f of j omega, when n equals 1 it is f j omega minus omega naught, and for each value of n you have a particular coefficient. So, if you take n equals 0, the portion of this corresponding to n equals 0 will be a d upon t n equals 0, this is equal to 1 sin theta by theta when theta equals 0 is 1 f of j omega. If n equals 1, this becomes a d upon t, this is t naught, I am sorry, this all the way this is t naught, a d upon t naught sin omega naught d upon 2 by omega naught d upon 2 f of j omega minus omega naught. That is what we are having. So, this portion which corresponds to n equals 0 is a d upon t naught times f of j omega. And this is something else. This is a d upon t naught times this quantity is corresponds to this. So, we have seen now that the central portion of the spectrum is a d upon t naught times f of j omega, that is a reduced version of this. So, the implementation of this is straightforward. You have f of t, you can have a multiplier with Ps of t, and this is your f star of t. You put this a low pass filter and you get your f naught, which is a replica of your original f of t. This is the general what is called the sampling theorem, which is referred to in literature as sampling theorem. That is, a band limited signal can be recovered from its a sampled version where the samples are taken at regular intervals with a frequency f naught, which should be larger than 2 times the highest frequency component present here. In practice, because of the limitations of the low pass filter that we have, the design of the low pass filters, in practice you may need to have a sampling rate, employ a sampling rate which is higher than 2 omega h, even though in theory any sampling rate greater than 2 omega h will suffice, but in practice we may have to take 3 or 4 times the highest frequency component because of the limitations of your design of the low pass filters. To conclude our discussion of the Fourier transform methods, let me offer a few remarks at this stage. Ideally, the Fourier transform is obtained by integrating the f of t over an infinite interval of time from minus infinity to plus infinity. In practice, when you have a signal, it is normally of finite duration, and therefore the integration is to be carried over for the duration of the signal, and this poses no problems. But on the other hand, if you have a type of signal which is continuous infinitely long for an infinitely long signal, and you would like to find out its Fourier transform in practice, you may not be able to have an analytical description of the signal, then in such cases what we can do is we can statistically process this information. That is, if you take a finite length of the signal, like for example a speech signal or so, take a finite length and find out its frequency characteristics and where the energy lies in which portion of the spectrum and so on, and it turns out that the statistical processing of the signal is quite a useful one. That means even if you take other samples of the signals, the essential character of the spectrum does not change. Therefore, this way it is one can handle signals even though they are need not be known for an infinite length of time. A second point which I would like to emphasize once again is that the Fourier transform method enables us to find out the transient behavior of networks and systems essentially using steady state methods, which we have emphasized once again earlier when we were working on the problems. That is, what we are trying to do is we are considering the transient excitation as the sum of infinite number of tiny sinusoids, and we find the response to each sinusoid using essentially steady state methods, frequency response methods, and add all the responses together to find out the total response. When I say summation, it is actually the integration that is being done, because these are all a continuous band of frequencies that we are having, but the principle is the same. Summation is essentially an integration. Integration is essentially a summation. Now, it is this fact that transient behavior of networks and systems can be analyzed on the basis of steady state sinusoidal theory that places this Fourier transform method and Fourier theory at an important, gives it an important place in communication engineering. In communication engineering, essentially we have to deal with transient signals and transient processing of transient signals, but the communication networks can be characterized in terms of their steady state behavior under sinusoidal excitation conditions, and using that information we will be able to process the behavior of these networks under transient signals. And some people assert that this is one of the most important ideas in communication engineering is the way in which we tackle these transient signals by the Fourier transform method. Now, we have also seen that the Fourier transform method, we have taken networks and found out the transients in the network using the Fourier transform methods, and we mentioned that we have certain restrictions earlier, not only on the type of excitation signals which can be handled by the Fourier transform method, and we also said we have placed some restrictions on the networks also. The natural response of the network should die down with time for the Fourier transform method to work in a convenient fashion. Now, there are several such restrictions when we apply the Fourier transform method to the transient solution of networks and systems. A competitor to this is the Laplace transform method, which we will take up later. For the Laplace transform method offers greater convenience for the analytical solution of the transients in networks and systems, mainly because it enlarges the class of time functions which it can be handled. That means certain types of functions like e to the power of 2t, for example, cannot be handled by the Fourier transform method, but Laplace transform method can handle this. Secondly, the several delta functions which you may get in the Fourier transforms are avoided when you use the Laplace transform method. Because of these reasons, Laplace transform method is a more convenient tool for analytical evaluation of the transients in linear systems. At the same time, where the networks are characterized in terms of their frequency behavior, in terms of their frequency response conditions, like communication networks, like filters for example, the Fourier transform method is a very convenient tool, because these frequency response characteristics of systems and networks can be experimentally determined. H of j omega can be experimentally determined. H of s may not be so easy to experimentally determine. So, where the networks are characterized by their frequency response behavior, then Fourier transform method turns out to be a very convenient tool to employ. For example, the behavior low pass filter that we have discussed a little earlier. Also, in certain branches like a control engineering and so on, it is the frequency response of a system that we are interested in. To assess the stability of a control system, sometimes we would like to know the frequency response characteristics of this. So, in such cases, of course, the Fourier transform method and the handling of the various components through the frequency response approach turns out to be very convenient. There are also well defined methods where once you know the frequency response, you can calculate the transient response graphically. So, because of all these reasons, Fourier transform method plays a vital role in analysis of networks and systems. But as I mentioned, for the transient analysis of networks, perhaps the Laplace transform method is a more useful tool, and that we will take up later. But nevertheless, as I mentioned, wherever the networks or systems are characterized by their frequency response, Fourier transform method turns out to be a more convenient tool. At this stage, we will I'll give you a set of problems as an exercise for you to work on the Fourier analysis, Fourier transform method. Now, let me write down a set of problems for you as an exercise under the topic Fourier transform and the Fourier integral. Let us consider an f of t which has got this type of variation t minus t, this is a, this is f of t. Find the Fourier transform of f of t in two ways. A, directly through integration, applying the standard formula for the Fourier transform, that is minus infinity to plus infinity f of t e to the power of minus j omega t dt, that type of integration. B, by first finding the Fourier transform of the second derivative of f of t. The motivation for this is, if you take the derivative of this, you get a pulse here and another pulse here, and if you take the second derivative, you have impulses, 3 impulses. To find out the Fourier transform of the impulse is quite easy. So, you find the Fourier transform of the second derivative of f of t, and from that deduce the Fourier transform of the original function f of t. Problem number 2. Consider the voltage signal e to the power of minus a magnitude t, a being a real positive constant. A. Find the Fourier transform of v of t this is the voltage signal v of t. Let me say this is v of t. Find the Fourier transform of v of t and sketch the magnitude spectrum. B. Calculate the available energy of in V of t, in the signal V of t. What do we mean by the available energy? If this V of t was applied to a 1 ohm resistor, what is the energy dissipated in that resistor V of t, in the resistor R? That is what is meant by available energy V of t. That is energy dissipated in a 1 ohm resistor to which V of t is applied. See, if V of t were applied to a 1 ohm resistor through a low pass filter, with a cutoff frequency omega c being equal to A, what would be the energy dissipated in the resistor? That is, you have a low pass filter which cuts off all frequencies beyond omega c, omega greater than A, then what is the energy dissipated in the resistor? Find the inverse Fourier transforms of the following functions: A, f of j omega equals 1 for omega magnitude less than 1, 0 for omega magnitude greater than 1. B, f of j omega equals 6 pi upon j omega. C, f of j omega equals minus j pi signum function of omega. D, f of j omega equals a set of impulse functions periodically occurring at intervals of omega naught. E, f of j omega equals 10 upon j omega plus 1 times j omega plus 2. That is the third problem. Fourth problem: find the Fourier transform of a function f of t defined as 1 for t between 2n and 2n plus 1 and 0 for t between 2n minus 1 and 2n, where n is ranges from minus infinity, minus 1, 0, 1 etc. to plus infinity for all integral values of n positive and negative. That is the fourth problem. Let us consider two functions f1 of t is a pulse of amplitude 2 lasting from minus 2 seconds to plus 2 seconds, and another f1t, f2t lasting from minus 1 to 1 second of height 1 unit. Find g of t, which is obtained by the convolution of f1t and f2t, and sketch g of j omega, which is the Fourier transform of g of t. Sketch g of t, that means magnitude and phase. Or we will change this, we will find g of j omega and sketch the spectra. Find g of j omega, sketch the spectra of g of j omega. Sixth, we have a circuit in which there is a voltage source Vi of t impressed across a circuit like this. This is 1 Henry inductor, 6 ohms resistor, and this current is I naught. The inductor carries 0 initial current, carries no current, no initial current. That is, before the excitation is applied, the inductor is carrying no current, and we are asked to find the current I naught of t for the following excitations. Vi of t equals 9 delta t, b Vi of t equals 9 ut, c Vi of t equals 9 e to the power of minus t ut. So, this is the sixth problem. This is the transient analysis of this problem. 7, the system function of a linear system is h of j omega equals 2 plus delta omega plus 1 over j pi omega. Find the response of the system to an input delta t, that is impulse response of the system is asked to be found out. That b, find the response to an input which is equal to t multiplied by e to the power of minus t ut. So, in both these cases make use of the system function, find out the input Fourier transform, multiply them out, you get the output Fourier transform, find the inverse Fourier transform, you get the response. We have not found out in this class, we have not discussed the Fourier transform of functions this time, but you should be able to derive them using the from fundamentals. T e to the power of minus t ut will have a Fourier transform which is 1 over j omega plus 1 whole square, that you should be able to derive.